we were looking at general systems and then focused on a subclass, namely LTI, and within LTI we are interested in the class of systems described by linear constant coefficient difference equations. And one of the reading exercises for you is to look up Oppenheim and Schaefer's Signals and Systems section 2.4 to see under what conditions does an LCCDE represent an LTI system, under what condition is it also causal. And we classified systems in terms of the duration of the impulse response. We looked at FIR, finite impulse response, and then IIR, infinite impulse response. And let's continue that discussion. So the general LCCDE is of the form y of n is k going from 1 to cap n a k y of n minus k plus k going from 0 to cap m b k x of n minus k. And then we made the point that if all the AKs are 0, then the system is FIR. Then we also made the point, if the system is IIR, then at least one AK is non-zero. And then the very last question that we were left with at the end of the last lecture was, if at least one AK is non-zero, is the system IIR. So, if at least one AK is non-zero, is the system IIR is the question. If the system is IIR, then surely you need at least one AK to be non-zero. Now, to answer this question, let us consider this particular example. So, let us consider y of n, and what this system is going to do is, it is going to take n contiguous samples, average them and then give out one number. Therefore, y of n is 1 over n x of k, k goes from n minus cap n plus 1 to n. So, this is what the system is, the input output relationship. So, you can see that this is nothing but 1 over n. So, this is x of n plus x of n minus 1 up to x of n minus cap n plus 1. So, all it does is, it takes n contiguous samples, averages them and then puts out one number. So, y of n is given by this. So, clearly the above equation can also be written as k going from 0 to n minus n plus 1. So, now in this form, this is recognizable as the standard form of an LCCDE, and here what about AK? Say that again. Yeah, I am sorry. K going from 0 to n minus 1 x of n minus k. You are right, thank you. So, now what about ak? They are all 0, and bk, it is 1 over n. So, clearly this system is FIR, all right. Now, let us rewrite this system in a slightly different manner. What is y of n minus 1? Y of n minus 1 is nothing but 1 over n x of n minus 1 plus x of n minus 2 up to x of n minus cap n. All I have done is, in this equation, wherever n is there, I have replaced little n by little n minus 1. So, this is what y of n minus 1 is. Now, let us express y of n in a slightly different manner. So, y of n can also be written as y of n minus 1. But if you look at the expression of y of n minus 1, you have this term 1 over n times x of n minus cap n. The last term that is there is not present in y of n. Therefore, we need to get rid of this extra term. So, you can subtract x of n minus cap n, but what is missing is the very first term, that is 1 over n x of n is missing. So, we need to put that back in. So, this is plus 1 over n x of n. Now, the intuition behind rewriting like this is that all you are doing is you are averaging n samples, and when a new sample comes, you do not have to recompute the average from scratch. All you need to do is update the average. So, this is updating of the average. So, this is the old average. You throw out 1 over n times the last sample and then add in 1 over n cap n times the latest sample. So, this is updating the average without having to recompute from scratch. Now, in this form, you see that AK is one. Remember, AKs are the coefficients of terms like this, y of n minus k. So, here actually I should call it as A1. A1 is 1. A1 is 1, right? So, this is minus 1. Was that the question? Yeah. Because in the form we have minus. So, A1 is really minus 1. So, this is what is called recursive implementation. It is recursive because you take y of n, delay it by one sample to get y of n minus 1, and that is fed back into the system. So, this implementation, what is called as a recursive implementation, because the current output y of n in this implementation also depends on the previous output. but this does not convert the system which was FIR into an IIR system. The system continues to be exactly the same as before, and we convinced ourselves that this system is indeed FIR. But in this implementation, it has feedback and A1 is -1. But this does not make the system IIR. That is the point. Therefore, the question that we asked, if at least one AK is non-zero, is the system necessarily IIR? Here is an example that shows that that need not be the case, that there can be systems in which you may have some AKs to be non-zero and yet the system can be FIR. We will revisit this later. We will talk about poles and zeros, and we will talk about uncancelled non-trivial poles. And later we will make the statement that if the system has an uncancelled non-trivial pole, it necessarily has to be IIR. So, we will revisit exactly the same example moment we introduce Z transform, and then we will talk about poles and zeros, and then we will talk about trivial and non-trivial poles, and then we will make the statement that this system will be definitely IIR if there is an uncancelled non-trivial pole. An LCCDE can be used to model physical systems. Let us consider this particular example. Y of n is A times y of n minus cap m plus x of n. This is a very simple difference equation. So, we will let A to be 0.98, m we will take it as 100, and then x of n we will make it as a uniform random variable between -1 and +1 for this. Then we will look at what y is and then see whether it reminds us of something that we have seen or heard before. So, let me implement this in MATLAB. Remember, the input has to be uniform random variable for 100 samples, and that uniform random variable is between -1 and +1. So, x is, I am going to use the MATLAB's rand function, and rand function gives me a uniform random variable between 0 and 1. Therefore, I need to convert that to be between -1 and +1. Therefore, what I am going to do is very simple here. So, rand gives me uniform, rand n will give me Gaussian, normal distributed random variables. So, you need to look up rand and rand n in MATLAB. So, here I am having 100 samples. So, if x is uniform between 0 and 1, 2 times x minus 1 will be uniform between -1 and +1. And then after all, I am going to let only the first 100 samples to be uniform, the rest I will make it as 0. Therefore, I will form a vector 44,100 samples. The first 100 samples are x, which are the random variables we have just now generated. Then I am going to implement this difference equation. So you need to look up the MATLAB command filter. A filter has the form filter b comma a comma x. So b are the b coefficients of the LCCD that we have seen, a vector of coefficients. A, again a vector of coefficients corresponding to the a coefficients in the LCCDE, and x of course is the input. Okay, so filter, and then the b coefficients is 1. As far as a is concerned, so this is the filtered output. Now let me plot y. So this is how it looks. This is the output of the difference equation, with the first 100 samples being random between -1 to +1, and then the rest are all zeros, and this input has been fed to this system with these coefficients. Now what I am going to do is I am going to play this. Sound SC will take the vector y, and sound SC will actually scale it. MATLAB expects the vector to be within a certain range. If you just use the sound command, if you have not scaled it properly, you may either exceed the MATLAB's expected range, or the scaling, if it's too small, the volume will not be loud enough. Whereas if you exceed the range, you will start to get clipping. So sound SC will take care of the normalization so that it's within the maximum range possible. So y is a vector, and then the sampling frequency is 44,100 is what I'm going to use. Let me play it again. Okay, what does it remind you of? It reminds you of a plucked string, right? So it certainly reminds you of a plucked string. So now remember, this parameter m was there. So you can play with this. You can either make it larger or smaller. So now let me make it larger and then see what effect that has on the quality of the output. So now I am again going to filter it. Rather than using this particular value, I am going to now give it a longer delay. So now let me has the frequency increased or decreased? Decreased, all right. So now you can expect what will happen if instead of increasing the delay, if I reduce it. So this is a shorter delay, so now it looks like a plucked string, except that it has a higher frequency, all right. All right, now let me see if I can play this. Okay. So now Rupak Vignesh was a student in computer science some time ago when I taught the class. He was there and then this kind of excited him. So what he did was take this difference equation and then he varied the parameters and then created this sound file. Repeated applications of this difference equation, that's all, nothing more, nothing less. The only thing he did was vary the amplitude and delay. Okay, so clearly this looks like a stringed instrument that's being played. So it kind of gives you an idea as to what you can do with such a simple-minded thing as a simple difference equation. This you need to look up what's called the Karplus-Strong algorithm. If you're curious to learn more, please look up the Karplus-Strong algorithm. So in music synthesis, signal processing is used very heavily, and this, even though it sounds good, very impressive and all that, it's still not quite what you can use to sell commercial instruments, right? So this needs to be refined and other things have to be added so that the quality is of commercial standards. I mean, you cannot just using the simple-minded thing, you cannot hope to make a synthesizer and hope to make money. You need to refine this. Plus this after all is only a stringed instrument. So this needs to be improved upon. Plus you also need other things like percussion instruments and so on. So you need to model those. So those are modeled and then they are generated using in hardware, right? So a DSP algorithm generates all these things. So in music synthesis, signal processing is very heavily used, and this kind of gives you a feel for what can be achieved.